Greetings, everyone. So what I'm going to record for today and what we're going to learn today is the use of the substitution method in processing or determining the solution of first-order differential equations. So allow me to share my slide. So this will be our last topic for first-order differential equations. And like the 6 topics that were discussed before this, in those 6 topics, our first-order differential equation has to first conform to a particular form. That way we can categorize it as in the case of separable, in the case of linear, and Bernoulli's equation. And for others, there has to be a test to be done. So that's in the case of the homogeneous DE and the exact differential equation. So that's where you're going to use the technique turning your inexact DE exact. If that is after the testing, you have found that your differential equation is not exact. Now, you can use under the inexact method, that was the second to the last discussed topic, the options wherein you can use the integrating factor or you use what we call as the definite differentials or the exact differentials. Okay, so those just but a review. Now, the reason why I was mentioning those, it's because for this last topic of ours on first order differential equations, using the substitution method, there's no need for us to conform to a particular form. That way we can classify our first order DE as such, and there's no need to do any test. So what you're going to do is inspect the terms, the functions that appear in your differential equations, if they are somehow related, or if one is the derivative of another. So you are to look for, if I may say, relationships between terms and functions that you can find in your differential equation. Now, to illustrate the use of the substitution method, we have these two differential equations here. So in here, in the first one, you have x plus 2y minus 1, dx plus 3 times the quantity x plus 2y dy equal to 0. If you start checking from the top down, so you ask if this is separable. This is not separable. If you check this is homogeneous, this is not homogeneous because of this one. If you check this is exact, this is never exact. Now, if you try to convert this to a linear differential equation or to a Bernoulli equation, it can never be in this case for this particular DE. So since this is inexact, you can try to make it exact. But as I have discussed to you in a second to the last discussion topic, the process is quite long because you have actually 3 possible options. You have 2 options for use of the integrating factor and 1 option for the use of the exact differential. So for now, let's say I won't use that particular technique of turning my inexact DE exact. I'll try to check whether substitution will work for this particular DE. The same thing with the second one, which again, just like the first here, we're going to start on top, starting with separable, homogeneous, exact, linear, Bernoulli. This one will never fall in any of those categories. So then you may try to make this exact if you want to, or you can try the use of the substitution method. So I'd like to start with the first one in here, and let's start with the clean slate here for our solution. Okay, so the first one that was given to you in that set of slides, excuse me, class. So let me try to write the first one that was given in that particular slide in our presentation. So we started with this DE. So I have started asking myself whether this is separable, homogeneous, exact, linear, or Bernoulli. And on the answer to all those questions is a no. So then I will try to check whether there are relationships in my terms here, if there are similar group of terms, or if there are similar terms, and probably I can use the method of substitution. In this case, class, if you look very closely, you see this x plus 2y here on the coefficient of the differential of x, and you also see an x plus 2y here on the differential of y. Since you can see both of these expressions in the coefficients of our differentials, we can assign a new variable for these two terms x plus 2y. So let's say we let x plus 2y equal to z. So the next thing that we're going to do is we differentiate this particular equation. So differentiate all the terms here based on the variables that you see. So you have dx plus 2 dy equal to dz. Then from in here, I can decide which of my differentials I keep and which one I change into something. Okay, so it would be easier to keep the differential of x, and I'll change or shall I say, I can change the differential of x into a representation in terms of dz and dy, because in my equation, I could see that dx is equal to dz minus 2 dy. What I'm doing here is that I'm going to replace the differential of x here by this set of expression, and I'm also going to change the x plus 2y by z. Okay, so I will do that. So for the first coefficient here, I can have z, x plus 2y being z minus 1. Then I'll change the dx here to this one. And for the second term, I will have 3, and then I have x plus 2y, which is z. Then I have dy. So the purpose of representing the two terms in here in the original DE by one variable is for me to simplify the original DE by simply representing these two groups of terms by one variable. Now, if you do that, however, we added a new variable in our differential equation. And it's not possible that in your differential equation, you should have 3 variables. You should only have 2. One is the unknown function or your dependent variable, and one is the independent variable. So as I have mentioned a while ago, I will decide, or I have decided that I keep the dy and the dz, and I'll change the dx into an expression of dz minus dy. Now giving me a differential equation now that does not contain any x, but rather has the variable z and the variable y. Now I will expand this, or I was, shall I say, group the terms that have the same differential. So I will distribute this quantity x minus 1 in here. And of course, there's nothing to distribute there because there's only a single term. Then I will group the terms that have the same differential. So if I do that, I will have z minus 1 dz. In the case of this one, multiplied to this. And then I have here minus 2 z minus 1 dy plus 3z dy equal to 0. Now, in my expansion, I am seeing two terms that have the same differentials dy. So what I'll do, I'll group the terms, these two terms into one. I need to combine the negative 2z plus 2 to 3z. Okay, so I'll do that. So I have the z minus 1 dz. And if this is a minus 2z plus z, so that would be a z. And this is minus 2 times negative 1, that would be plus 2. Then it's multiplied to dy. So you can see that my original differential equation, which doesn't fall on any classification, or is not proved to be homogeneous or exact after testing, is converted into this form. So I have a z minus 1 dz, in this case of this one, And I have here z plus 2, quantity z plus 2 plus dy in case of this one. Now you can see that this is right away. So right away, this is separable. So let's go to the next page and process our separable DE. Now, all I need to do is transfer the quantity z plus 2 in here on this term. That way I can integrate this one. Also the same thing with this. So I will just do that by, before we go to the next page, by dividing my new differential equation by z plus 2 because I want to eliminate quantity z plus 2 on the second term. So now, for your first term, you will have a z minus 1 over a z, I forgot what's there, over a z plus 2. Dz. And on the second term, you have dy left because these two will just cancel each other. So you have dy equal to 0. So being separable, now you can perform integration separately for your two terms. Now this one, the rest of the process here is your integral calculus. So your z minus 1 over z plus 2 actually, based on the rules of integration, have the same degree in z. So what you do, you divide the numerator by the denominator. So you'll have 1 and you'll have a z plus 2. And when you subtract, you will have here a minus 3. So your first term here actually is the integral of, for the 1, you have the dz. And for this remainder, you have minus 3 integral of dz over z plus 2. This is your negative 3 remainder. So it would be negative 3 over z plus 2. And that's your second term. For this first term here that you need to integrate. And you have the integral of dy equal to 0. So if you will further integrate, you have the z, and this one is an ln of z plus 2. And you have here a y. And if you recall our discussion regarding the presentation of the arbitrary constant when one of the terms in your answer of the integral is an ln. So since I have an ln here, I will write my arbitrary constant as an ln of z. And then I will transfer this ln here that I have on the left side, on the right side, because I have another ln here. So I will have z plus y being equal to ln c plus, so this becomes plus already, 3 the ln of z plus 2. Then I'll simplify this one. Sorry about that. Okay, and I will simplify this one by making the coefficient 3 here as the exponent of the z plus 2. So on the next page, we will have now something like this. We have a z plus y equal to, so you have here ln of c. It's being added. So it's being added to this one. So what is this particular property of the ln if we have addition? That's equivalent to multiplying the arguments of this ln. So I will now combine the two ln's into one ln expression. So I will have the ln of c. We have times because I have here addition. So meaning these two arguments will be multiplied. So the 3 becomes the exponent of this expression. So that would be z plus 2 raised to 3. So I'll have here c plus 2 raised to 3. Okay. Now, I will write this particular solution explicitly in terms of y. So I will write here y is equal to ln, or rather, sige, you will have c times z plus 2 raised to 3 minus z. So I have written it explicitly in terms of y. The thing is, we don't have the z variable in our original DE, so we need to go back to the original and check what the z represents. So z is x plus 2y. So you're going to change all the z here in your answer to x plus 2y. So y is equal to ln of, so you have c times x plus 2y plus 2 cubed. The z was replaced by x plus 2y minus the quantity x plus 2y. Okay. In here, you could see, class, that it's impossible or it's difficult to write your solution explicitly in terms of y because the argument of your ln here has also a y variable. So the best that we could do is simplify only. So this is negative x minus 2y. So I'd rather place the minus 2y in here. So this becomes 3y positive because this makes it positive equal to the ln of c times x plus 2y plus 2 raised to 3. Okay, you have that. And of course the x, so minus x. Now, if you want to transfer the 3 in here, that could be done. So you have y is equal to 1/3 times the ln of c times x plus 2y plus 2 cubed. And then you have minus x. Now, this is the solution of our given differential equation, which we solve, the process of substitution. Okay? Now, this one does not contain any transcendental function. It's only the x and y variable. What about if we work out the second example wherein you already have the presence of a trigonometric expression? So what is this particular differential equation that was shown to you a while ago at the start of the discussion in the form of a PowerPoint presentation? So this particular DE is actually 1 plus 3x sine of y dx minus x squared cosine of y dy equal to 0. Now again, you have to ask, this is a parabol? Is this homogeneous? Is this exact? Is this linear? Is this Bernoulli? The answer again is a no to all of those. So it doesn't fall on any of those. So now you try to check if it's possible to use substitution. Now this time, if you look for similarities, you don't find any. So there's no similarity in here. There are no group of terms that are similar. But if you look very closely, you could see relationships. Now this sine y function, if you differentiate it, it's actually cosine y dy. So now we will use this particular relationship between sine and cosine function. That way we can use the substitution method for our second DE. So we will do that. I will assign again, just like in the first example, I will assign a new variable to the sine of y. If I will differentiate this again, so every time you assign a new variable to represent a group of terms or a function, the next thing that you do is you differentiate. So dz, and this one becomes cosine of y dy. So I'll go back to my DE and substitute this z and this dz to this expression. So I will have 1 plus 3x z, and you have the dx, and in here you have minus x squared dz, okay, equal to 0. Okay, your x squared, and you change the cosine of y dy to dz. Now, if you look closely at this new differential equation, this is not homogeneous, this is not separable. Let me check. This is not exact, I'm sure, but we can check whether this will fall on the linear or Bernoulli equation, knowing that it's so easy to transform this DE into one that has the derivative, the unknown function, and another set of terms. Okay, so we will do that, class. Okay, so that's it. I need to stop because my laptop ran out of power. So you have this now. So we're going to check whether this is linear or Bernoulli equation. So we will try to represent our derivative. So our rule in representing or specifying our derivative is that the differential that has the simplest coefficient should be on top of that derivative. So in this case, if our derivative should be a dz dx. So I will divide by dx. So what remains after division would be 1 plus 3xz minus x squared dz dx equal to 0. This is far from being linear or Bernoulli in terms of form, so I'd like to transfer this one in here. That way it becomes positive, and I will transfer as well by division the presence of the x squared as a denominator of this one. That way my derivative will have a coefficient of 1. So I will divide by, I can do also division by negative x squared. That way my derivative becomes positive already. Okay, so in our next slide, we will have now a dz dx. So it becomes now minus in the sense that my division is negative. So this one makes it positive for this, and I have x squared here as the divisor of 1 plus 3xz. So I will have here 1 plus 3xz over x squared equal to 0. So I just rearrange it that way. I can check right away if I have a linear Bernoulli equation. So 1 plus 3xz over x squared, and it's negative. Now, it's a requirement for linear or Bernoulli that the next term after the derivative should be the product of your unknown function, the unknown function, in this case that would be z, and an expression in terms of the independent variable. So my unknown function is only present here on the second term. So if I will distribute x squared as a divisor for this two, I will have this now. So I will have 3 over x, because the x here and 1x here will cancel each other, and it will be multiplied by z. This one will be negative 1 over x squared, and I will transfer it on the right side. Then that makes it positive. Now, the way it looks now, it's now linear. So this is your derivative. This is your p of x. This is your q of x. So it's linear because you don't have the unknown function here raised to an exponent other than 0 or 1. Okay? So if it's linear, what do we do with if it's linear? We determine the integrating factor. So our integrating factor phi is e raised to the integral of, so this is negative 3. So I'll place it here, and I will have a dx over x. This gives us an e raised to negative 3 ln of x. This is e raised to the ln of x raised to negative 3, which is actually 1 over x cubed. With that as our integrating factor, we use the formula for linear DE, which is the unknown function. This time it's not y but z, times the integrating factor 1 over x cubed should be multiplied to the integral of the q of x, which is in this case 1 over x squared. So I will have 1 over x squared. You will multiply to this the integrating factor phi, and then integrate. Now, in this side, it's a z over x cubed, while this side will require the use of the power rule. So this is x raised to negative 5. So it becomes x raised to negative 4 over negative 4 plus c. Now, what is z in the first place? Because we don't have z in our original DE, so it has to be replaced. So it's the sign of y. So we go back here and replace our z by the sign of y. And we multiply our entire equation by x cubed. So I'm merging two procedures here so that we will not have a very lengthy solution. So the z that is remaining here after multiplying the entire equation by x cubed is your sign of y. And you have this one now. So if you will multiply by x cubed, this becomes x raised to negative 1 over negative 4 plus cx cubed. Or we say that the sign of y, okay, is equal to cx cubed minus 1 over 4x. So x raised to negative 1 is 1 over x. And this is your 4. The negative sign is it is 1. So this is the solution of our D using the method of substitution. Now, if there's a question that might be crossing your mind as to what is it specifically in your DE that tells you that right away when it's given to you to solve, you will know that this is to be processed using the method of substitution. There's no clear-cut rule class, there's no test, there's no form. So just like in integral calculus, it takes a lot of practice. That way you will know that your particular given integral, or in this case, your particular differential equation, will fall on any of the category or can be solved using the other techniques that were taught in the subject. So you have to do a lot of practice. But my suggestion is, after now knowing 8 possible ways of finding the solution of your first order differential equation, you start from the simplest. So whenever you're given a DE, you ask first, is it separable? Next question, is it homogeneous? If the answer is still no, is it exact? If the answer is no, you go to linear and then Bernoulli. Actually, when you test in terms of the form, whether your DE could be linear or Bernoulli, it's just one test that you do. Then you can right away say whether it's linear or Bernoulli. Now, if your DE tested inexact, meaning it's not exact, and you want to make it exact, then you have to use the two possible options. The use of the integrating factor or the use of the exact differential method. Okay, but that one is not suggested because again, it entails a lot of practice in terms of manipulating your equation. That way, you will have a resulting exact differential in your groupings. At the same time, the other terms are rendered integrable. Now, if all else fails, meaning after you have asked yourselves question whether those are applicable for a given DE, and your answer is still a no, then that's the time that you're going to use the method of substitution. Okay, so this ends the techniques and the classification of first order differential equations.